A hand passes over this small, domed sensor, and a second later, an alert hits a smartphone on the other side of the world. High-end security systems often require expensive hardware and recurring subscription fees to provide this capability. You can replicate that functionality yourself with less than $10 in off-the-shelf parts. Most DIY tutorials have a major flaw. They fail the moment your home Wi-Fi drops. We are going to write failure-resistant code that allows this device to survive router reboots and network outages automatically. To build this, you need a NodeMCU ESP8266 microcontroller, an HC-SR501 PIR motion sensor, a few jumper wires, and the free Arduino IDE software on your computer. By combining these basic components with robust logic, we are building a 24/7 security tool you can actually trust to protect your home. The system relies on two core parts. The ESP8266 acts as the brain, processing logic and connecting to the internet, while the PIR sensor acts as the eyes, detecting the infrared heat radiating from moving bodies. Wiring takes 3 cables: VCC to the 3.3-volt pin, ground to ground, and the middle data pin to GPIO 13, labeled D7. On the back of the sensor, turn the time delay dial fully counterclockwise to its minimum so it resets immediately after detecting motion. The physical circuit is complete, but it is currently isolated from the world. To make it useful, we have to build a bridge from this local hardware to the global internet. We will use a free service called IFTTT. This platform acts as a translator, taking a basic electrical signal from our board and converting it into a push notification or email. Setting up the logic is simple. You create a new applet and set the if-this trigger to use the Webhook service. Then you set the then-that action to send an email to your inbox. To link our board to this applet, we need credentials. On the Webhooks documentation page, you will find a unique alphanumeric key and a specific URL string assigned to your account. That URL is the exact digital address our ESP8266 will call the moment it detects an intruder. With the cloud infrastructure waiting, we can now program the microcontroller logic that actually pulls the trigger. The baseline code is straightforward. We define D7 as our input pin and then pass our home network credentials to the board so it can establish its initial Wi-Fi connection. Inside the main loop, the board constantly reads the sensor's state. When that state goes high, the board fires an HTTP GET request directly to our IFTTT URL. However, PIR sensors require about a minute of power to calibrate to the ambient infrared levels of the room. If we ignore this, the sensor will fire false triggers the moment the device first boots. We fix this by inserting a mandatory 30-second delay into the setup block of our code. This forces the board to wait while the sensor stabilizes before it enters the active monitoring loop. This code works perfectly in a testing environment, but it possesses a vulnerability that makes it unreliable for real-world use. If your home router reboots or the Wi-Fi signal drops for even a second, the default ESP8266 code will freeze. It loses the connection and hangs in a loop, leaving your house unprotected. We add an auto-reconnect block that checks the Wi-Fi status. If dropped, it fires disconnect and reconnect commands. But using a standard delay function here is a mistake. Instead, we use the non-blocking millis function to track elapsed time. A delay command is blocking, meaning it forces the entire processor to halt for 10 seconds. During that window, the processor ignores the PIR sensor, effectively blinding the security system. The millis approach is non-blocking. It acts like a background stopwatch. The board checks the time, moves on, and keeps the motion detector fully active while the Wi-Fi silently heals itself in the background. Replacing a blocking command with a non-blocking timer ensures the PIR sensor never stops watching the room, regardless of what the network is doing. With the finalized code uploaded, open the serial monitor. Pass your hand over the sensor, and you will see the successful trigger logged on screen, followed immediately by an email arriving in your inbox. Now for the ultimate stress test. We will simulate a total network failure by physically cutting power to the local Wi-Fi router. The board immediately senses the outage. The serial monitor displays the connection loss and initiates the reconnect loop, constantly attempting to find the missing network. When the router is powered back on, the system automatically re-establishes the connection and resumes watching. It requires zero human intervention to get back online. Because this logic is so stable, you can pack the board into a project box for a stealthy alarm, or use the exact same trigger logic to automate staircase lighting when someone walks by. You now possess a self-healing IoT sentry that maintains its own connection. You can find the complete code in the description below. Grab your parts, compile the sketch,